Good afternoon. So today's colloquium speaker is Federico Gasperini, who is our most recent ASP postdoc. Federico has a background in aeronautical and aerospace engineering, did his bachelor's in the University of Pisa in Italy, and a master's at the University of Southern California, Los Angeles, before coming here to CU Boulder to do his PhD on wave coupling as viewed from quasi-sun synchronous satellites. He briefly left Boulder to go to do a postdoc at the Utah State University before returning here in April this year to start his ASP postdoc. And today he will tell us about whole atmosphere perspectives on connections between intra-seasonal variations in the troposphere and thermosphere. Thank you.
Thank you. Thank you very much, Brian, for the introduction. Thanks to all of you for coming. So as Brian just mentioned, the title of my presentation is A Whole Atmospheric Perspectives on Connections Between Intraseasonal Variations in the Troposphere and Thermosphere. And in this presentation, I will show results that will take advantage of both the satellite perspective, in particular the timed Goche and Champ satellite observations, but also models, in particular the timed GCM developed here by HAO and also MERA reanalysis data. And I'll show briefly some results also that take advantage of the newly developed WACAM-X 2.0. So a brief overview of or outline of my presentation is the following. In the first part of my talk, I will cover some of the background information for some of you who may be less familiar with some of this material. And then the second and third part of my presentation will focus on examples of wave coupling from two quasi-sun synchronous satellites, the timed and Goche missions. And then the third part is the evidence of tropospheric 90-day oscillations in the thermosphere, which is really what I'm focusing my current work. So starting with the background, variability in the thermosphere, we have sources from above, such as the absorption of solar UV radiation, and also joule heating and particle precipitation, which are mainly high-latitude processes. But really in the last decade or two, evidence has demonstrated that a lot of the variability in the ionosphere and thermosphere is due to terrestrial weather or meteorological processes. And the way that that occurs is through the propagation of upward propagating waves. And as I wrote here, the primary mechanism through which energy and momentum are transferred from the lower atmosphere to the upper atmosphere and ionosphere is through the propagation of waves. So to describe wave coupling in the atmosphere and ionospheric system, I'm showing here this illustration from the Solar and Space Physics Decadal Survey, and in particular from Jeff Forbes, that shows you in green the lower atmosphere, whereas in gray up here we have the ionosphere and thermosphere, and in red we have the mesopause. So there is a group of waves that have different spatial and temporal scales that are being generated by different processes, such as orographic instabilities for the so-called gravity waves, the absorption of solar radiation for tides, but also a latent heat release in convective clouds. But in particular, the subgroup of these waves is capable of propagating upwards, and as they do so, their amplitude grows exponentially with height. And so those waves that are capable of propagating all the way up to the lower thermosphere and above can dissipate and accelerate the mean flow, and so essentially coupling the lower atmosphere with the upper atmosphere, but also ionosphere, either in the E region or in the up here in the F region. There are other processes that I won't describe here in the interest of time, but these waves can also interact non-linearly within each other, and I'll show some examples of this in my presentation. So atmospheric waves are generally grouped in 4 different classes. We have gravity waves, Rossby planetary waves, solar tides, and Kelvin waves that have different spatial and temporal scales. We have the gravity waves that are fairly limited in the time scale and also spatial scale up to only a few hundred kilometers. Then we have the global scale waves, and in particular for my presentation and my work, it focuses on solar tides and Kelvin waves that I'll describe in further detail in the following slides. But the reason why I focus on these two group of waves is that they're global scale waves, and they're responsible, they're known to be responsible for coupling the lower atmosphere with the upper atmosphere and ionosphere. So solar tides are primarily excited by the absorption of solar radiation by different layers of the atmosphere. We have down here by water vapor, up here in the troposphere, in the stratosphere and mesosphere. We have absorption of radiation by ozone as a primary mechanism, and higher up in the lower and upper thermosphere, we have the absorption of ultraviolet and extreme ultraviolet radiation by molecular and atomic oxygen. But the heating rate can be imagined to be schematically the following, where we have no heating during the night and only heating during the day. So the heating rate can be decomposed in a mean, diurnal, and semi-diurnal component, which you can imagine that heating occurs in different regions of Earth, and that generates a spectrum of tides, which are generally described as a summation of cosines, where the amplitude of the cosine is a function of z, which is altitude, and theta, which is latitude. And the argument of the cosine has n omega t, which is the frequency of the tide, and s lambda that describes the longitudinal dependency of the tide. And for a diurnal tide, a tide that has a period of 24 hours, n will be equal to 1. S is the zonal wave number, and it's assumed to be positive to the west in this notation. And again, that describes the longitudinal variation of the tide. And phi is the phase. So we'll have a summation of tides that goes from n equal to 1 to big N, which usually is assumed to be up to 3. So we only generally consider up to 3 diurnal tides. Those are the ones that have periods up to periods of 8 hours. And the zonal wave number minus k to plus k, usually we assume it to be plus or minus 4 or 5. The speed at which the tide moves in the east-west direction is the phase, the zonal phase speed, and that is equal to n omega over s. And you will notice how if n is equal to s, the phase speed will be equal to the rotation rate of Earth. Essentially, those are the so-called migrating tides, and those are the tides that migrate westward like the sun does. But the ones that have s different than n, those are the so-called non-migrating tides. And a lot of the literature in the last couple of decades has demonstrated the importance of these non-migrating tides to generate variability in the ionosphere and thermosphere. Another point that I'd like to make here is that this expression for the spectrum of tides becomes the following if we are in a constant local time frame. And you'll see that the only difference is really the longitudinal dependence that is no longer dependent on the zonal wave number s, but is a difference between s and n. And so that plays an important role in some of the results that I'll describe later, because this is what we are looking at from a fixed local time perspective from space on a sun-synchronous orbit. A few more details on solar tides. Their standard nomenclature is the following. We have DWX or DX to denote westward or eastward propagating diurnal tides, where X is replaced by, or denotes the zonal wave number. So for a DW1, that's the diurnal westward 1 tide. If instead of having diurnal tides, we have semi-diurnal or tridiurnal tides, then S and T replaces D. One of the largest tides that has been shown to propagate all the way up to the thermosphere that is thought to be primarily generated by tropospheric convection is the so-called DE3. So that's the diurnal eastward propagating tide with zonal number 3. It has been shown to be the main driver of the observed wave 4 or 4-cell structure in the ionosphere and thermosphere. and it is a large source of variability in the MLT. And important to note is that also its first symmetric mode is a Kelvin wave, so it has no meridional speed, and it is also confined primarily at mid-low latitudes. And I describe this in a few words here now because I'll show some results for this tidal component in the following part of my talk. Another global scale group of waves that I previously mentioned are Kelvin waves. Those were first observed in the atmosphere by Wallace and Kowalski in '68. They propagate eastward, similarly to D3, and also upward. And similarly to D3 also, they're believed to be primarily excited in the troposphere by convective heating. And they have been shown to be a large source of, or an important source of coupling between the lower atmosphere and the middle and upper atmosphere. They're generally grouped in three classes, depending on their period. We have slow Kelvin waves, fast Kelvin waves, and ultra-fast Kelvin waves. Now, for my study and for this presentation, I'll only show examples of ultra-fast Kelvin waves that have periods up to 6 days, and those are the only ones that are known to be propagating all the way up to the thermosphere. An additional source of variability that I previously mentioned is nonlinear wave interactions. So as we have two primary waves described by cosine dependent on the frequency and the zone wave number of the wave, those that can interact in a nonlinear forcing region, which you can imagine occurs in different regions of the Earth's atmosphere. And that interaction generates two secondary waves, for which the mathematical expression is the following, where you see that the frequency of the secondary waves are the sum and differences in the frequency of the primary waves interacting, and the zone wave numbers will be the sum and difference in the zone wave numbers. What is one of the important points here that I'd like to make is that secondary waves will have a different frequency and zone wave number than the primary waves, and therefore will be affected differently by the dissipation and the mean winds, for example. And so one wave might propagate higher up than others because will be affected differently by the background. And I'll show some examples of evidence of nonlinear interactions in the thermosphere in the following few slides. But before I get there, here a few details on how do we generally observe the wave field. There are ground-based methods. Incoherent scatter radars are one kind that provide MLT temperatures and winds between 100 and 120 kilometers, but are primarily limited to campaign intervals of up to 10 days or so. Then we have resonance lidars that provide temperatures and winds, both day and night, but also not continuously. Then we have MF and meter radars provide winds between 80 and 100 kilometers. And then we have also passive optical methods that provide MLT temperatures and winds, but primarily restricted to nighttime. So the main advantage of looking at ground-based measurements is that we have ability to distinguish waves over very short periods of time, and also we have information on the vertical structure of the wave. But of course, the main disadvantages are, as I wrote here, the lack of information on latitude-longitude structure. So we are limited on where the instrument is located. And in addition to that, we also, or because of that, really, we are not capable of distinguishing between global and local scale waves. And if we're talking about tides, we are not capable of distinguishing different tidal components. So for my research, I mainly focused on space-based methods, in particular on quasi-sun-synchronous satellite measurements. Those satellites are polar orbiting, and they have an approximately constant local time. And so the higher the inclination, generally, the slower the precession period, or the slower the precession period is, in such a way that if we have an inclination of 96 degrees or so, we are in a sun-synchronous orbit, and so that's a fixed local time. So essentially, the advantage of using satellite data is that we have a global coverage, but also the fact that we are using the precession period of the satellite to have all the information on different tidal components. We have to average over what the precession period of the satellite is, which can be several months. So the main disadvantages of using satellite data are grouped in sampling and aliasing. Sampling are due to the inherent variability of the atmospheric system within the 24-hour local time coverage. So if it takes 130 days for the satellite to cover all local times, the tidal or wave features that we'll be able to resolve are generally will be a multi-monthly mean. And also we have the issue of aliasing, which is that zonal mean and other longer period waves can alias into the derived tidal field and are perceived as local time changes. So since I'm seemingly running a little bit late in time, I'll jump right into my the first part of really of the results that I'd like to show here. So for this part of my talk is called wave coupling from timed and gauche, and here I'll demonstrate vertical propagation of two global scale waves that are being primarily generated in the troposphere, and I will also demonstrate evidence of nonlinear interactions between these two global scale waves. These results are based on my 2015 and 2017 JGR paper and 2017 JSTP paper, and I'd like to acknowledge Jeff Forrest, my PhD advisor, and also Maura Hagen, that are co-authors in these studies. So the data that I've used are timed SABRE temperatures around 110 kilometers. SABRE is an infrared radiometer on board this NASA satellite that provides still measurements of temperatures between 20 and 120 kilometers or so, and it was on a slowly precessing, or it is on a slowly precessing orbit. Whereas Gauche is an European mission that was launched in 2009 and re-entered in 2013. And for this study, I used neutral densities and winds that are measured on board from a very accurate accelerometer at approximately 260 kilometers. And I focused my study on the 3-year period between 2010 and 2012, focusing at mid-low latitudes. Essentially, the SABRE data provides data at 110 kilometers in the lower thermosphere, whereas Gauche gives us data in the middle thermosphere. I'll spend a few words on the methodology that I've used. Essentially, I've fit the Gauche data to a solar and geomagnetic proxy, and I removed those fits so that I could concentrate better on the signals due to waves. I've extracted daily tidal amplitudes using the so-called ascending node differences, and I'll describe this in just a moment. And also I've analyzed nonlinear interactions using pseudo longitude spectra, and I'll describe those also in the following few slides. But here you see magenta, the S10.7. This is a proxy for solar UV radiation similar to the F10.7. And the AP, 3-hourly AP, is in green down here for a particular 15-day window that I'm showing here as an example. So you have in black the Gauche winds, and down here in the Gauche densities. I performed a nonlinear square fit between the S10.7 in AP and the Gauche data, and I removed those fits from the raw Gauche data, so again, that I could concentrate on the wave signals. Now, one of the, as I previously mentioned, one of the disadvantages of using satellite or quasi-synchronous satellite data to analyze waves, and in particular tides, is that we have to average over all local times, which creates multi-monthly means. So to counteract that disadvantage, I have differentiated the measurements taken at the ascending and descending node. Here I wrote an expression for a tidal component at the ascending and descending node. And if we take a difference of those, of ascending and descending measurements, you can take advantage of the fact that the local time difference is approximately 12 hours to come up with this expression here, where essentially for each day we can fit a wave S minus n in the ascending minus descending divided by 2 residuals, and derive the amplitude and phase of the diurnal tide. In particular, this method allows for removal of the semidiurnal component. And so the advantage is that we are capable of extracting daily tides, but tides that have the same S minus n will alias into each other. And also there are errors if the nodes are not exactly 12 hours apart, in particular due to aliasing of the semidiurnal component. An example of applying this method to SABRE data, daily D3 amplitudes are shown here. You see plus or minus 40 degrees of the equator for the 3-year period. So you can see that D3 tends to maximize, in the post-summer months, but you also see a lot of this day-to-day variability, which we wouldn't really be able to appreciate using the precession period of the satellite. Using the same methodology, I've also demonstrated that D3 is present in the middle thermosphere in the Goce data by performing a correlation analysis. Similarly, I've also demonstrated that an ultra-fast chem wave is present in the lower thermosphere, and that is also propagating all the way up to the middle thermosphere, as demonstrated by the Goce data. In addition, I wanted to investigate whether I could find evidence of nonlinear interactions between these two global scale waves. Again, here is a mathematical expression for how the nonlinear interaction occurs. So if we have an ultra-fast chem wave that has a period of 3 days, so a frequency of omega over 3, interacting with D3 that has a diurnal tide, so it has a frequency equal to the rotation rate of Earth. The two interacting will generate 2 secondary waves that have a frequency that is a fraction of a solar day. So essentially the problem here is that the signals are outside of the Nyquist limits of daily sampling. So if we order the data in daily, we would not be able to resolve these signals. And so in order to highlight and to demonstrate the existence of the secondary waves, I use the so-called pseudo longitude method, in which instead of ordering data in UT time, the data is ordered in longitudes. Essentially, as the satellite goes around one orbit, we have 15 orbits in one day. So we every time a revolution is completed around Earth, we add 360 degrees and create a time series that has longitude instead of time. And if we take a spectrum of such a time series, we are able to locate tides at peak. It will be showing as peak at S minus n, also planetary waves m minus delta, and the secondary waves due to planetary wave or due to planetary wave tidal modulation.
So,
sure.
In the previous two plots where you showed the Kelvin waves and the D3, from those time series, do you notice any correlation between the two?
Yes. In fact, in my study, I was performing a correlation that was focused around the equator to demonstrate that there was propagation. And the correlation coefficient are 0.67, I think, in one case, and 0.64 in the other case. So we think that perhaps the mean winds and dissipation could be some of the physical processes responsible for generating some of the variability that we're not able to correlate, between the two heights.
Even though the two may not have the same seasonal dependence, but they're still correlated.
Yes.
To the magnitude.
Yeah. So in this case, here is an example of a pseudo-longitude spectrum. So in this spectrum, you see at integers, you will see peaks due to tides, and anything in between will be due to either longer period waves or secondary waves. So here is this is an average for a 3-year period for SABRE temperatures at 110 kilometers. So you can see that there is evidence of a peak due to the ultrafast scan wave at 1.3 and also a peak at 4 due to the D3 tide. But in addition to that, you see also secondary wave peaks due to due to K1 and K2 at 2.7 and 5.3. Using the similar method for the Goche data, I've demonstrated that the secondary waves are also present there. And I've then extracted these signals in the time domain and demonstrated their importance in generating some of the day-to-day variability that we're interested in. So as I wrote here, spectral analysis of Sabre and Goche data reveals secondary wave peaks due to the interactions between these two global scale waves. And so the main conclusion for this part of my presentation is that vertically propagating waves really generate important variability or relevant variability in the low latitude thermosphere and larger than the contribution due to geomagnetic activity for solar low conditions. In fact, I haven't shown the second part of this statement in this presentation, but you can refer to my papers if you're interested in this. But here I've demonstrated a group of tropospheric waves, such as D3 and the ultrafast scan wave, can propagate from the lower to the middle thermosphere and account for significant thermospheric variability. Secondary waves that have been generated by the nonlinear interactions are also responsible for significant variability in the thermosphere. And lastly, what I wrote here in gray is a point that I didn't have the opportunity to discuss here, but I still like to make, is that performing these fits with the S10.7 and AP, I was able to quantify what the relative contribution is of upward propagating waves and geomagnetic and solar effects, and estimated that between 60 and 80% of total thermospheric variability could be traced back to vertically propagating global scale waves and their nonlinear interactions, and only 20% could be traced back to geomagnetic and solar effects, and up to 20% to unexplained processes. So here, the third part of my presentation, I will discuss evidence of tropospheric 90-day oscillations in the thermosphere. And these results are largely based on my 2017 GRL paper, and I'd like to acknowledge my co-authors, Maura Hagen and Yucheng Chao for their contribution. So the data that I've used are the following. I've used Goche cross-track winds that I described for the previous part of my presentation, and I've also used CHAMP cross-track winds. So CHAMP, similar to Goche, had an accelerometer on board that allowed the estimation of neutral densities, but also cross-track winds. So those are the winds that are in the east-west direction, and so those are the winds that are perpendicular to the direction of motion of these polar orbiting satellites. CHAMP was launched in 2000 and re-entered in 2010, and it provided very, very valuable measurements of both winds and densities. And these data are in the thermosphere at 260 kilometers for Goche and 330 kilometers for CHAMP. In addition, I've also looked at OLR, outgoing long-wave radiation data. This is a common proxy for tropospheric convection. And I've also analyzed time GCM numerical. I have taken advantage of a numerical simulation from the time GCM, which is the thermosphere, ionosphere, mesosphere electrodynamics general circulation model. In particular, the simulation that I'll show examples of in this presentation are forced at the lower boundary by MERA data, which is a NASA reanalysis data set that has a lower boundary of 30 kilometers and an upper boundary above 500 kilometers, and I'm mainly focusing on the zonal wind field. And the results that I'll show are largely are limited to the 2009 to 2010 period that was characterized by strong tropospheric convective activity. So here is a wavelet, a plot of CHAMP zonal wind at 330 kilometers and CHAMP D3 tidal amplitudes that shows periods between 20 and 120 days, and it is for 2009 and the early part of 2010. And it clearly demonstrates a very strong 90-day oscillation. If we then look at Goce at 260 kilometers, slightly below, we see evidence of a similar 90-day oscillation in both the zonal winds and DE3. If we then look at the time GCM model, that also shows a 90-day oscillation in both the zonal winds and DE3. If we then look at AP and F10.7, we see no evidence of a 90-day oscillation, which essentially suggests an internal source. So to better investigate what that could be, I've analyzed the time GCM simulation further, in particular on a height versus time domain. Here I'm showing the zonal mean wind on the left panel and the 3 tidal amplitudes in the zonal wind in the right panel. And you see there is a lot of day-to-day variability in D3. You also see the semi-annual variation in the zonal mean wind. But you can also somewhat resolve what looks like a 90-day oscillation in the zonal mean wind up here. So to better highlight that 90-day oscillation, I used the 85 to 95-day bandpass filter and filtered this data set. And what you can see here is that there is a strong 90-day oscillation in the thermosphere that is both present in the zonal mean winds and in D3. And it has amplitudes up to plus or minus 20 meters per second in the winds. But really the breakthrough of my study was to analyze OLR data, which is a proxy for tropospheric convection, and reveal evidence of a similar 90-day oscillation in there. So here the top panel is showing in blue OLR that is averaged plus or minus 30 degrees off the equator. And it shows you here on a periodogram a very strong peak at 90 days. And if time GCM, of course, has that 90-day oscillation in there. And then I filtered these data sets and looked in the time domain and demonstrated that there is a correlation between the 90-day oscillation in OLR and in the model, correlation coefficient of 0.71 for the model, for CHAMP 0.63, and for Goce 0.59. Also, I'd like to point out here the phase relationship that there is between OLR and time GCM, and somewhat also in the observations. So one of the recent developments that I'm currently working on is looking at Hofmüller plots, which are showing essentially time here, and in the y-axis and on the x-axis we have longitude. These are OLR anomalies that are 30 to 100 day filtered, and these essentially show, for example, in this case that I've highlighted in red here, is an MJO event, which is propagating eastward. That's a Madden-Julian oscillation event. Essentially, it's a tropospheric, it's an anomaly that is propagating eastward with a speed of 5 to 15 meters per second. And so, of course, part of my study is now trying to demonstrate if that 90-day oscillation can be connected to the MJO. So what I did recently is to bandpass filter that OLR for 85 to 95 days, and you can see here OLR and here time GCM around 30 kilometers, and there are some similarities between the two. But more interestingly, analyzing the WACAMX 2.0 model for the same time period, 85 to 95 day filtering at 15 kilometers, shows some very interesting and similar structures between OLR and WACAMX 2.0. So part of my study is now trying to see whether I can demonstrate an eastward propagation of this wave that could be connected to the MJO. So in summary, I've analyzed CHAMP and Goce cross-track winds to reveal the existence of a strong 90-day oscillation in the thermospheric mean winds and D3 during 2009 and up to 2010. I've used MERA time GCM to demonstrate that the oscillation is coherent with height, and it is now propagating from below as a wave. Also, OLR reveals that the same 90-day oscillation is present in tropospheric convection, and it correlates with observed and modeled thermospheric winds. A similar but localized 90-day oscillation has been also observed in the mesospheric temperatures. I'd like to acknowledge, in fact, Yu-Cheng Xiao at Utah State University, who first introduced me to work on 90-day oscillations in the thermosphere. And so our results suggest that tides and gravity waves are modulated by tropospheric convection at a period of 90 days, and they're transferring this periodicity to the lower thermosphere by dissipation and energy momentum deposition. Of course, there is a lot of work that has to be done to prove this point. But my study still demonstrates that there is a strong coupling on intraseasonal timescales between the troposphere and the thermosphere. And of course, that motivates my current work that I'd like to spend a few words to describe. Essentially, the motivation, part of the motivation for my current work is that the 90-day oscillation has not only been observed in the thermosphere, but has also been shown to be a very strong signal in the sea level data over the equatorial Indian Ocean during 1992 to 1999. I'm showing here this plot from Han 2005 that you can see in the bottom left panel. And also 90-day oscillations were observed in lower thermospheric CO2 radiative cooling between 2002 and 2006 by Martin Linktuck 2008 paper. And also more recently, Kunago in 2013 showed this wavelet plot of 4 champ magnetic wire residuals that demonstrates a very strong 90-day oscillation that occurs throughout the champ data set that is over 10 years of data in there. So the objective of my current work is to provide further observational evidence for correlative correlations between intraseasonal variations in the troposphere or from the troposphere up to the thermosphere, and investigate potential explanations for these connections using the WACA-MAX 2.0 model that is currently being refined here at HAO. So the following science questions to be addressed are the following. The first is how frequent, prevalent, and persistent are correlations between intraseasonal variations that have periods between 30 and 100 days from the troposphere to the mesosphere up to the thermosphere within the past 15 years when we have CHAMP and GOCHA data. Also, how well does the WACA-MAX 2.0 model capture the observed intraseasonal variability from the troposphere up to the thermosphere? And what plausible roles do large-scale, global-scale waves play in coupling the lower atmosphere with the, in particular, on intraseasonal timescales out to the thermosphere? But of course, there are a lot of other questions that I'm trying to address. For example, as I previously mentioned, is there a connection to the MJO for the event that I just described? And also, is there a connection to the ionosphere as well? With that, I'd like to thank you for your attention. If there are questions that I'm not addressing here, feel free to email me at that email address. Thank you.
Any questions today before you email? Nick?
So you estimate that the lower atmosphere is like 60 or 80%, which seems almost double what has previously been quoted, which is more like 30 or 40%. Right. Is there a reason for the sort of discrepancy? Is it how you arrive at this number?
Yeah, that's a very good point. So in that study, I was focusing on a very solar low and geomagnetically quiet period of time, and the study was only performed in a few 15-day windows. So it might have been that the contribution in that period of time of very low solar conditions, the contribution of tides was larger than what has been previously shown. But I would like to analyze a longer period of time to better address that.
So you're not saying that's the sort of typical number? That's
right, no. Right, it's, yeah.
Let's go behind and then I'll come to Dolores next.
Oh,
So.
all right. It looks like this is exactly 92 days. Looks like a quartannual harmonic of the seasonal force signal rather than free tropospheric weather. Do you think that's the right takeaway?
That's a good question. We looked into that, but what's to us interesting is that it's not. It doesn't seem to be a subharmonic of any superposition of the seasonal and annual variability. So I would not imagine that that's just caused by the superposition of longer and shorter.
Isn't it exactly a quarter of a year?
It is, yes.
Terannual. I don't know what word comes after terannual, but is it?
Right.
You know, when you have a seasonal cycle that's truncated, it takes all the harmonics are hit by the sharp edges of the.
Right.
Yeah. I wonder if it's just a harmonic or if it's free.
It is. It's not in a harmonic.
Okay.
I've looked into that. We can probably discuss this offline, but yeah.
Federico, several times you mentioned that you were looking at kind of a narrow band around the equator. Is that generally true, or are you seeing this kind of signal at all latitudes?
The 90-day signal is primarily limited around plus or minus 45 degrees of latitude. I've analyzed the global structure, filtering the data in that sense, and it seems to be primarily at mid-low latitudes. And it is interesting that some analysis shows me that seems to be concentrated around the Indian Ocean area, which could be, due to the MJO, but certainly not at higher latitudes than plus or minus 45 degrees or so.
And that is because you have actually explored that space, and it is
right. Yes, yeah. I've for the entire year of data, I've essentially filtered the 90-day oscillation on a global perspective, and I have an interesting plot that I don't know if it's in my background slides, but it is not, but I can provide that to you. It's also in my GRL paper that is actually showing where the oscillation seems to be concentrating within a global perspective.
So back to the question, the comments you made earlier about the 90 days shown in the SABRE data. I believe that Melinda's study is a globally integrated power. So I think it's lots of signatures come away from the equatorial region. So yeah, but if the 90, MO with this oscillation is limited to the equatorial region, then it will not be that obvious in the globally averaged power.
That is true.
Specifically the global integrated power.
That is true, yeah, that's an interesting point. But the MJO is not only restricted, as far as I understand, to the equatorial region, but it can affect, a broader range of latitudes.
So in the Hopf-Muller diagram you showed, I was wondering if you can go back to the first one showing, I think it's the lower, the OLR.
Mm-hmm.
It just from that plot, it seems that the 90-day oscillation, it seems it's only existing in part of the year, or I was just wondering how persistent that signal is, the previous plot.
Oh, in this previous plot?
Yeah, this one. From here, it seems it's, at least that 90-day eastward propagation is very limited, or limited to a certain time of the year. But I wonder how persistent is your upper atmosphere signal is.
Right. So I'm still trying to investigate what the signal looks like higher up. And now, for that particular plot, what's really interesting to me, more so than the how long that occurs throughout the year, is the regions that oscillation occurs in terms of longitude, which are primarily here in this region up to 180 from the east. So that's primarily where the MJO, as I understand, occurs. But in terms of when the oscillation occurs in time, so you can see here that it seems to be mainly concentrated towards the second part of this data set that I've analyzed, which is coherent with some of the results that I've showed earlier.
So you make the comment that this oscillation is similar, the Wacom X2 at 15 kilometers
Right here, yeah.
something similar? Does that mean that Wacom X is producing the MJO?
Well, that's something that I'm working on right now. I produced this blog last week, and but yes, that's what it seems like to me, as far as I can tell, in this case. But of course, one of the interesting things to me is that we see that the MJO would be propagating eastward, whereas here we have, for example, that which looks like a westward propagation. So it's not really clear to me at this point.
So this is the free run or the nudged?
The notched.
Not nudged. So it is from mirror.
So it has the mirror at the lower boundary, so we could expect the MJO. In fact, there is a study that demonstrated the MJO effect on DW1 using the same model simulation.
Any more questions? Let's thank Federico again. Thank you.